Hello everybody, so in this video we're going to go over what the mean value theorem says. We'll look at what it means graphically, and then we'll go over the proof of the theorem. Okay, so we're going to start off by giving the statement of the theorem. So let f be a function that satisfies the following. Okay, and again, we're going to have three different hypotheses. Okay, f is continuous on the closed interval AB. The second condition is that f is differentiable on the open interval. Okay, and then the third condition is, oh, there is no condition. Okay, then let's look at our conclusion. There exists a number C in the open interval AB so that, okay, f prime of C, right, the derivative at that point is equal to, and then let's take a look at what this is equal to. Okay, so this is going to be f of B minus f of A divided by B minus A. Okay, so what does that mean in terms of the graph? Okay, so let's go ahead and look at a graph. Okay, so let's have our A value be right here. Okay, and we'll have our B value be here. Okay, now unlike Rolle's theorem, it's okay that these are not equal in value. Okay, now what is f of B minus f of A over B minus A? Well, that is the slope between these 2 points. Okay, so we would say that f of B minus f of A over B minus A, okay, is the slope of this line that's drawn, okay, which is the secant line. Right, just the line drawn between the two endpoints. Okay, and remember f prime of C is the derivative of the function or the slope of the tangent line. Okay, so we are looking for a place where the slope of the tangent line is the same. Right? So this would be my value C. Okay? So this is this is the tangent line, okay? I don't want to say it's the slope of the tangent line. Okay, so what we're seeing here is that at some point, the secant line and the tangent line are parallel. Okay, so this is really what the mean value theorem means, right? It's also called mean in terms of average, right? Because we're taking the average value here. But this is showing that this value, which is the slope of the secant line, is equal to the slope of the tangent line at some point, right? Equal slopes meaning parallel lines. So at some point, the secant line is parallel to the tangent line, okay? And that point where they're parallel, that's the C value that we are talking about, okay? So now that we kind of graphically understand what this is telling us, let's look at a proof of this theorem. Okay. Now, the most important thing for us to remember when we're looking at this proof is Rolle's theorem, right? What we just went over, because that's the main thing that we're going to use here. Okay. So the first thing we're going to do is define this function g of x. And we're actually going to define it to be the tangent line. Oh, I'm sorry, the secant line. Right, this is the slope of the secant line times x minus a, right, plus f of a. All right, so this is how we're going to define our function g of x. Okay. And then we're going to say that we know that g of x is continuous and that it's differentiable. Okay, and specifically, g of x is a linear function, so we know that it is going to be continuous and differentiable everywhere. Okay, and then we're going to define another function, h of x. Okay, so this is just going to be the function f that's described in the theorem minus this function that we just defined, g of x. Okay. Now, we need to say why h of x, we want to try to use Rolle's theorem, okay? So we need to say why h of x satisfies the conditions of Rolle's theorem, or the hypotheses of Rolle's theorem, right? So we know that the first one is that it's continuous, okay? So h of x is continuous. On the closed interval because it is the difference of two continuous functions. This is one of the things that we studied in chapter 2 when we talked about continuity, is that the sum and difference of two continuous functions is also continuous. Okay, and this is a very similar reason to why h of x is differentiable. Okay. It's differentiable on the open interval because It is the difference of two differentiable functions. Okay. And then the last thing is we want to check what h of a is and what h of b is. Okay, so h of a is going to be f of a minus g of a, right? And we remember we know what g is, right? So this is going to be f of a minus f of b minus f of a over b minus a, right? Times a minus a plus f of a. Okay, now a minus a is going to be 0. So this whole term in the center is going to be 0, right? This whole thing here, this whole term will be 0 because a minus a is 0. Okay, so I have this, and then I'm going to have, right, I still have my minus sign, f of a. Okay. And then I'm going to look at h of, oh, I'm sorry. We need to finish up what this is. So f of a minus f of a is 0. Okay. And then I'm going to look at h of b. Okay. So this is going to be f of b minus g of b. Okay. And I know what that means. So I have h of b equals f of b minus, okay, and then g of b is going to be f of b minus f of a over b minus a, okay, times b minus a plus f of a. Okay, now what's going to happen over here, right, is that this b minus a is going to cancel with this b minus a. Okay. So this is going to be f of b minus, okay, now all I have is the numerator of this fraction, which is f of b minus f of a. Okay, and then I still have this plus f of a. Okay, now this minus f of a is going to cancel with this plus f of a. Okay, so these two are going to cancel out. This one, oops, this one and this one. Okay, and that's going to leave me with f of b minus just f of b. Okay, so h of b is also 0. Okay, so we've defined this function h that meets all of the criteria of Rolle's theorem, right? It satisfies all of the hypotheses of Rolle's theorem. Okay, so let's make some space and then we will talk about what happens when you apply Rolle's theorem. Before I erase that, I just want to point out that you absolutely should say, so h of a is equal to h of b. Okay, that's what we're getting from saying that h of a and h of b are both 0. Okay. So now that we have that, again, right, we know that it's continuous on the closed interval, it is differentiable on the open interval, and that the endpoints are equal. Okay, so we would say by Rolle's theorem, okay, there exists a C so that h prime of C is equal to 0, right? That's what we know about Rolle's theorem. So let's look at what h prime of C is, okay? So remember, h prime of x, or I'm sorry, h of x was equal to f of x minus g of x, okay? And g of x was f of b minus f of a over b minus a times x minus a plus f of a. Okay. So if we want to look at the derivative, h prime of x, right, this is going to be f prime of x. Okay. Now this whole thing, this whole fraction, this is a constant, right? The only variable is x. So when we take the derivative of this, right, this is just like if we had 3 times x minus 2, right? This is just going to be f of b minus f of a over b minus a, right? This is the coefficient of x, so that's going to be the derivative. Okay. So what does it mean for h prime of C to equal 0? Okay, so h prime of C is going to be f prime of x, or f prime of C, I'm sorry, minus f of b minus f of a over b minus a. Okay, so that's h prime of C, and this is going to be equal to 0. Okay, so what that means is that f prime of C is equal to exactly what the theorem says, right? F of b minus f of a over b minus a. Okay. So we really are relying heavily on Rolle's theorem to give us a way to prove the mean value theorem. Okay. But when you think about the mean value theorem, you should be thinking about the graphical interpretation where the secant line, or the line between the two endpoints of the interval, is parallel to the tangent line. Okay? In the next video, we will talk about some examples of the mean value theorem, so I will see you guys there.